Hi, in this session I'm going to talk about probability. Now, probability is something that we use quite often without thinking about it. For example, if we think about whether it is going to rain today, we might look at the clouds, or we might look for the clouds in the sky and say, if we see a lot of cloud, we say probably. If we just say see a few clouds, we would say maybe. And if we don't see any clouds at all, if the sky is completely clear, we would say definitely not. So when we say maybe, probably, definitely, certainly, or definitely not, or never, in a mathematical sense, these are really expressions of probability. Maybe not in a precise way, not with a hard number, but these are probabilities. It tells us how likely something will happen, and this is what probability is about. It tells us how likely something is going to happen. Now, in the mathematics of probability, we will learn how to put these I can call it feeling of whether something is likely to happen, how to put this feeling into a definite number. So we are going to learn how to calculate, for at least for simple cases, how to actually find an actual number that tells us this probability. So let's start with example using a coin. Right, it depends on which country you're in. Coins are different from country to country, and even within the same country from year to year. And there are two sides to a coin, and it is often that we talk about the two sides and call one side the head and the other side the tail. Now, I do not know the reason for saying that, but whichever country you're in, let's just call one side of the coin head and the other side the tail. So there's a coin, and if you flip the coin over, you see the other side, and they would usually look different. They might have a different picture or carving on them. I'm just going to call one side the head, represented by the letter H, and the other side by the tail. Now, if I take this coin and I toss it and it falls on the table, it's usually difficult to know whether it's a head or a tail before you toss it. Alright, if you really toss it, that is, just throw it up and allow it to fall on the table and bounce a few times and then fall flat. So we don't know which side faces up. So it can be a head or a tail. But we can think about the probability, for example, of getting a head. Let me write that down. So head is head, right? That's H stands for head, and T stands for tail. Alright. The probability of getting a hit. And the way to calculate this is to think about all the possible outcomes of the toss. So we can either have a head or a tail. So there are, in this simple example, two possible outcomes. Now, these two outcomes, at least in this example, assuming that we have a normal coin, nothing special, and if you toss it, there is no reason why you're more likely to get a head or a tail. It's not as if one side might be heavier than the other side and come down first. So let's just assume that when you toss it, it's equally likely that you'll get either one, head or tail. Alright, and so there are two possible outcomes, two possible events. But we are interested in the probability of getting just a head, which is one of these events, one of the two possible events. So the way to calculate the probability of getting a head is to write down the number of possible events that might happen. In this case, it is the head. Alright, so there's only one possible event that we are interested in. So what we do is we take the one possible event, which is getting a head, divide by the total number of possible events. So that's the way to calculate probability. Alright, we count the number of times, number of possible times that, not times, but the number of possible events that we have listed them out, the one that we are interested in. Okay, in this case it's the head, so it's just one out of the two possible events, and we put a 1 on top of a fraction, and then we count the total number of possible things that can happen. So in this case it's 2, and I put it down there. So that's how we do it. And this idea of calculating a probability is something that we can use in all kinds of examples. So before I move on to another example, let me summarize this idea into a formula. Now I'll write this as probability is equal to the number of events let me write it this way. The number of interested events, those that we are interested in, like in this case the head, okay, which is just one of them, divided by the total number of possible events. And in this example of the coin, there are two. There are only two possible events, the head or the tail. You can't have anything else when you toss a coin. So what we have here is a formula. Now let's try to apply this to another example. Right. Let's look at a die. Now that's a rather strange name if you are seeing it for the first time. But a die is not die as in living or dying. In this example, die refers to a little cube with either numbers or dots on it that you toss. Looks like this, and there are many types. Well, one common type is one with dots on it. I have a dot there, maybe 2 dots there, 4 dots there, and so on. So there are different number of dots on the different sides of the die. And just let me write down another form of this word. Dice is the plural of this word die. Alright, so in this case, we are using the word die not as in living or dying, not as a verb, but we are using it as a noun to mean this object. Alright, and the plural of that is called dice, D-I-C-E. The probability, right, now if I throw a die, again I just toss it high up and it falls and it lands on the table after bouncing a few times maybe. And only one side faces up, and that side can have either 1 dot or 2 or 3 all the way up to 6 dots. That's the usual way a die is made. And assuming that it is a fair die, now there's this idea of fairness coming in, either a fair die or a unbiased die, meaning that it is equally likely for the die to land on any side. Now actually, there is such a thing as a biased die. Right? It happens that people who gamble and cheat when they are gambling might put a little bit of metal on the inside of one side of the die. Alright, but maybe a side with a bigger number, so that or the smaller number, so that it is more likely to land on a particular side. So that's a biased die. A biased die, it would be more likely to give you some particular number. So in our example here, we are just going to look at a fair or an unbiased die, which is equally likely to land on any side. So it's equally likely for us to get any number from 1 to 6, or any number of dots from 1 to 6. Right. So suppose that I am interested in the probability of getting a number of getting, say, the number 1. No, right, I'll make it 2. Getting alright. So I can use this same formula to find the answer. First of all, I should think about the number of interested events. Now in this case, events, the word event here, refers to the number the numbers that I can get from the die. So that's 1 to 6. So I can have 1, 2, 3, 4, 5, 6. So there are actually 6 possible events, meaning that the total number of possible events is actually 6. In fact, I can put that down first at the bottom. Right, there are 6 possible events. Now we are interested in the possibility, the probability of getting a 2. Now 2 is just one of the 6 events. So the number of interested events is 1. And there I have my answer. The probability of getting a 2 is 1 over 6. So we've just seen how to use this formula in this other example. Now before we start thinking that the number of interested events is always 1, let me just change this question example a little bit to make it slightly more complicated. Rub away the 1. So I'm still looking at the same example with a die that I toss, an unbiased die. Now this time, I'm interested in the probability of getting an even number. Right. Now an even number means 2, 4 or 6. So you see, in this example, it is a bit more complicated than the one just now. This time, my number of interested events is bigger, right? Because there are now 3 even numbers. So that's the number of interested events, because I am interested in the number of even numbers, and there are 3 of them. So there are 3 events that I'm interested in. So I think of each of these possible outcome as an event. So because there are 3 interested events, I put a 3 up there. And that's my probability, 3 over 6, which is half. So the probability of getting an even number is half. So now that we have seen these 2 examples, let us go back to the everyday usage, the way that we like to use probability every day without even thinking. For example, if I'm still looking at this die, okay, now as the probability of an even number, sometimes we might actually be able to get the right answer without thinking. For example, if you want to talk about how likely you can get an even number when you toss a die, it is probably obvious to you that because there are 3 even numbers and 3 odd numbers on a die, it's equally likely. Okay, and because it's equally likely, you might just say the probability of, or maybe not in such a mathematical way, you might just say that when you toss a die, you would get an even number half the time. Alright, because 3 over 6 is half. But you don't have to do this calculation or use this formula to know that. You might just know it because there are just the 6 numbers and half of them are even. So you might say, when I toss a die, I would get an even number half the time. And I would get an odd number half the time. So that's an expression of probability. You're actually saying that. Or if we go back to the example just now about tossing a coin, you might say that if I toss a coin, I would get a head half the time. Now then, when you say that, there is another idea that you're actually using unconsciously. And that's the idea that you may not be thinking of just tossing the coin or the die once. When you say half the time, that sort of means that you're thinking about tossing it a few times or many times. So if let's say you toss it 10 times and you count how many times you get a head when you toss a coin, you might think that half the time you get head. But actually, if you toss a coin 10 times, it's very unlikely that you will get a head exactly half the time. Meaning that if you toss a coin 10 times, it's very unlikely that you will get a head in exactly 5 of the 10 times. You might get 4 heads out of the 10 times, or 6, or even something different. But you are likely to get something that is close to 5. Now from the example just now, what we have seen is that we have this formula in which probability is equal to the number of interested events divided by the total number of possible events. Right. If you look at this, the number of interested events can never be more than the number of possible events. The number of interested events also cannot be less than 0. Okay, so if I start imagining an event that is not possible, then the number of interested events would just be 0. Like if I think about when I toss a die, what is the probability of getting -1, a negative number, or of getting 7, a number that's more than 6? Then the number of interested events would just be 0. Alright? So the probability would be 0 if I have events that are impossible, like getting a 7 or -1 on a die. And I can talk about events that include all the possible events. Like when I toss a coin, I can say, what is the probability of getting a number from between from 1 to 6? Now, if you are talking about tossing a die, the numbers from 1 to 6 include all the possible events. So, the number of interested events would just be 6. Okay? And when you divide 6 by the total number of events, which is also 6, the answer is 1. So that is the biggest number that you can get in a probability, which is 1. So 1 means that it is certain, okay, that it will definitely happen. Okay, we can call it absolute certainty. Absolute certainty, or is definitely happen. So if you have a probability of 1, it will definitely happen. Like getting a number from 1 to 6 when you toss a die. Because you can't get anything else, and you will definitely get one of them. So the 0 and the 1 gives us the lowest and the highest value you can have in probability. And all the other numbers are in between, right? Like when you toss a die, the probability of getting an even number is half. So if you find that the probability is very close to 0 when you talk about an event, this you may say that it has a very low probability, and we use words like it is possible but improbable. So that's the kind of thing that we mean. We really mean that the probability is not quite 0, but it's a very small number. Or if the probability is very close to 1, we might say that it is probable or very probable. Right, and I just mentioned that there's this idea of the probability of success and the probability of failure. If you think about tossing a coin to get a head, then you might think of the head as a success, and if you don't get a head, it's a failure, right? Now the idea is that the probability of getting a head plus the probability of getting a tail must be equal to 1, because that includes everything. So we can think of this in a more general way and say that the probability of success plus the probability of failure must always be equal to 1, because success and failure includes all the possible events. Right. So, for example, if I have an example with a die, let's say I have an example with a box with a number of balls. have 2 red balls and 3 blue balls. It's not very good. So this is another example that is quite common. Let me just say I have 3 red balls and 1 blue ball. Okay. Now let's say this is a black box and you're supposed to put your hand inside without looking at what's inside and just pick up 1 ball, and all the balls feel exactly the same. So let's say we're interested in the probability of getting a red ball. Now you'll find that this is one common way to write down a description of the probability. So instead of writing it out in words, in full, and say probability of getting a red ball, so that's a lot of words to write out, we might just write a letter P to represent probability, and we put the word red in a bracket. Now if you remember from the last session on functions, this looks very much like the expression for a function. Alright, so the probability of getting a red ball, just P bracket red. So that's what it means. And if I want to find the probability of getting a red ball, I would use that formula. Okay. And the total number of possible events when I pick from here is 3, because I can get any of the red balls, because there are 3 balls. Now we have to be careful here. You mustn't think that the number of possible events are 2, because it can just be red or blue. Meaning that you should not count the number of red balls as just 1 event, because there are 2 red balls and 1 blue ball. Okay, so in fact, if you are picking them blindly, it is actually more likely that you pick a red ball than a blue ball, because there are 2 red balls. So you should really count the 2 red balls as 2 events, okay, and not just 1 event, because 1 is red, 1 is blue. So there are actually 3 possible events, because there are 3 balls, and of the 3 events, we are interested in the probability, we are interested in the red balls, picking a red ball. And the number of red balls is 2. So 2 is my number of interested events. Let us now find the probability that it is not red. That means that when we pick a ball blindly, that we get a ball that is not red. Now obviously, in this very simple example, you know that if it's not red, it is blue. And there's only 1 blue ball, and therefore the answer should be 1/3. But I want to show how we can use another idea to get the answer. Now the other idea is that, if you remember what I said just now, the probability of success plus the probability of failure must be 1, because that includes everything. So it's the same here. I can think of, because I want to pick a red ball, so if I actually succeeded in picking a red ball, then I can think of that as a success. But if when I pick a ball, it turns out not to be red, it's not red, then I can think of this as a failure. So success and failure is really just mean, it really means just one case or not that case. Alright, that something happens or something does not happen. So that's another way of thinking about success and failure. So success and failure, red or not red. So therefore, since I know that the probability of getting a red ball is 2/3. So the probability of not getting a red ball must be 1 minus the probability of getting a red ball, because the total probability must always be 1. So 1 minus 2/3 must be the answer. So this means that I can actually find the probability of not getting a red ball without thinking about the number of blue balls at all. So that gives us a quick way to find the answer for more complicated examples. The addition law of probability, that's what I'll look at now. Let's look at the example of a die again. So if I toss this die, I'm interested in the probability of getting, say, a 2 or a 5. So what's the probability of getting a 2 or a 5? Now we can do it directly using the formula, number of interested events over total number of possible events, and in this case the number of possible events is 2. So just 2 and 5. And that's very easy. The answer is just 2 over 6. 2 events divided by all 6 possible ones. Right, but there is another way to do it. We know that the probability of getting a 2 is 1 over 6, and the probability of getting a 5 is 1 over 6. And it turns out that the probability of getting a 2 or a 5 you can find by taking the probability of getting a 2 plus the probability of getting a 5, which in this case is 1 over 6 plus 1 over 6. So this actually gives us another way of calculating probability. It's not very useful in this example because it's so simple. Right? We already know it's 2 over 6. But it is very useful for more complicated examples where it's not so obvious, and if you already know the probability of the separate events, like of getting a 2 and of getting a 1, alright, so if in more complicated examples it's more difficult to find the probabilities, then you can use this method where you can just add up the probabilities if you want to know the probability of getting one event or the other. This is called the addition law. But there is one thing about this law that we must know, we can only use this law if the two events are mutually exclusive. Now that's a rather complicated word, mutually exclusive. What it means is that if one event happens, the other event must not happen or cannot happen. And if the other event happens, this event is not possible. So in this case, it's quite obvious. If you toss a die and you get a 2, then it's definitely not a 5. You can't have a 5 happening at the same time as a 2 when you toss a die. So we call this mutually exclusive. Now we might want to think of an example of two events that are not mutually exclusive. So one example might be if we have 2 die, alright, if you have 2 die and you toss the 2 die at the same time, and if you get a 2 on one die, you can also get a 5 on the other die. So if I have 2 dice, then getting a 2 on one and a 5 on the other is not mutually exclusive because they can happen together. So this is how to think about it. We can only use the addition law to find the probability of one event or the other event happening. We can only use this and simply add the probabilities if the two events are mutually exclusive. That means that they cannot happen at the same time. Multiplication law. This is another law that is useful. Let's look at the example of a die again. Now, what we'll do this time is that we'll toss the die, right, just throw it on the table. And suppose that when we toss it once, we are interested in getting a 2. And then after that we pick that up and toss it again. So we toss it a second time. And I'm interested in getting a 5. So I want to find the probability of getting a 2 on the first toss. That's my first toss. And my second toss, I'm interested in the event of getting a 5. So the problem here is to find the probability of getting a 2 and a 5. You must be a little bit careful here. Of course, it does not mean that I want to get a 2 and a 5 at the same time when I toss the die. Alright, if I just toss the die, I can only get one number. It means that I'm interested in getting a 2. The probability that I will get a 2 when I toss the die for the first time, and that I would then get a 5 when I toss it for the second time. So what is the probability of this? Right, I know that the probability of getting a 2 in the first toss is 1 over 6. A 5 in the second toss is 1 over 6. We can use a multiplication law to do this. The multiplication law says that the probability of getting a 2 and a 5 is equal to the probability of getting a 2 times the probability of getting a 5. And the answer is 1 over 6 times 1 over 6, right? Which is 1 over 36. So that's how we can calculate these two probabilities, this one probability. But there is a condition when we can use this. We can only use this multiplication law if those two events are independent. Now, independent means that independent means that one event must have no effect on the other events at all. And in this case, we can see that they don't have effects on each other, because when you toss one die, you get a number, and after that, if you toss it again, there's no reason why the outcome of the second toss should depend on the outcome of the first toss. Alright, they are separate events, and they don't affect each other. So it is only when two events has no effect on each other, it does not influence each other, it does not make the other more or less likely. It is only when this is true, when the two events are really independent, that we can use this multiplication law and find the probability of the two events simply by multiplying them. Now, what is an example of two events that are not independent? Right, an example might be, say, you can still look at the die. For example, if you have a die which is made of very brittle or very soft material, then after tossing the die for the first time, the die crumples a little bit. The die breaks up a little bit at one of the corners. Okay, one of the corners get chipped off after you toss it once on a hard table. So that is going to affect the outcome of the second toss, because the die's shape, the shape of the die has changed. So if you toss the second die, your answer would not be the same if you toss a good die. So in this case, the two events would not be independent. And of course, if we're talking about the die chipping or breaking up, things get complicated. So we won't go into that. We'll stop here for this session. See you next time.